Okay, hello and welcome to my channel. Today we're gonna talk about the Breit-Wigner distribution. So this would continue to talk about resonance, scattering, and quasi-bound states and those stuff. So this would be in scattering theory, the easy part of it. Okay, so first let's take a look at our tan delta first. Now we would assign this to be equal to beta over alpha minus k. So we jump to the k space. Now, so from here, get that your delta is tangent minus 1 beta over alpha minus k. All right, so now if you want to graph it, it would be this. So first, for your tangent delta, this would be k, as we are in the k space. This would look something like this. Be around the point alpha, you draw a line. And it's gonna go like this. This is gonna kiss the line A, or alpha, and here it's like this. Right. And the point, this where it jumped is most of the time pretty obvious to see. So this point, that would be alpha plus beta, and this is alpha minus beta. Okay, so there we go. This is your plot for tangent delta. Now take a look at our delta. So our delta would be something like this at a point, this point alpha. It's gonna go this, then suddenly jump up, and this point is where it hits the value pi over 2, and this would be pi here. So you see at this point resonance happened and it jumped a value approximately pi. So that would be how you would identify where the resonance happened and what would be the value of it. So these two plots would help you to identify those. Okay, so from that up here, you can get also your the delta dk at k equal to alpha would be equal to 1 over beta. Okay, next is our scattering probability density. This guy, we're gonna write it as sine square delta. As you remember, it is EI delta sine square delta, sine delta, and sine kx plus delta. This term, the maximum of it is 1. This term, when you square it, it gets to 1. And since we are trying to find the scattering part, so we would like to isolate and only take the scattering, the pure scattering stuff here, which is sine square delta. Sine square delta would be beta square plus alpha minus k squared. Right, so that would be your scattering probability. Okay, next we're gonna take a look at another graph. Yeah, I know you have to look at a bunch of graphs here. Okay, so next would be the graph. Okay, maybe writing the, okay, no, I will draw the graph first, and then we're gonna look at the formula or equation. Okay, so this graph would look like a bell. It's something like that. And maximum value is 1. And it would peak when energy, okay, it's pretty hard to see, but your energy here would be E alpha. And the relevant part that we want to take is this, called the half width of your distribution. We call this gamma, and gamma is equal to 2h bar squared alpha beta over m. Okay, so the end point and the start point of your gamma would be right. Okay, there's not enough space. Okay, so the starting point, I'll just write it here, and the end point of gamma be E alpha. Starting point is minus, that is minus gamma over 2. And endpoint is E alpha plus gamma over 2. Right, so this would be the distribution of your psi scattering. So here in this thing here, you write your psi scattering as 1/4 gamma square over 1/4, no, over E minus E alpha square plus 1/4 gamma square. 1/4. Yeah. So this would be your probability density for your psi s. Okay. And this one you can get your E minus E alpha pretty easily, as they have everything the same, just only the k square and the alpha square is different. So when you take E minus E alpha, and that would be equal to E alpha, that is h bar squared over m, k minus alpha. It's that simple. And you can do this computation on your own and maybe show it in a comment. I hope so. Okay, so from this distribution, we can get another thing, that is the lifetime, which is equal to h bar over gamma. The lifetime of your scattered wave, that would be m2 alpha beta h bar. All right, then you have your lifetime. Now one more thing you can do is compare it with your time delay. So your time delay, as you remember, is 2h bar, the delta prime, delta k prime. So we can split this into the delta k, delta e. Okay, and here as this guy we take the value at alpha for these, that would be 1 over beta. And this guy, well, remember, delta E delta K is, well, h bar K over M. So this, you flip it, M over h bar square over K. H bar square K. Okay, sorry. Okay, so from here, you compare that with your tau, and you can see that your delta T is exactly 4 tau. Right, so from this, you can get the equation h bar over gamma equal to delta T over 4. Okay, so that's it or the Breit-Wigner distribution for now. So goodbye for today. Next time we're gonna look at the complex K-space, which is one of the very cool thing that I really want to show you. All right, goodbye.